Hello and welcome to today's webinar, Pulsed Time of Flight, a complex technology for a simpler and more versatile system, brought to you by Vision Systems Design and sponsored by Teledyne E2V. My name is Chris McClune. I'm the Editor-in-Chief of Vision Systems Design, and I will be your moderator today. Our speaker today is Yoann Lochardet, Marketing Manager 3D at Teledyne E2V. This webinar is both live and interactive, and a huge part of these webinars is our discussion with you. So please ask questions at any time via the Ask a Question box in the presentation window. We will answer as many of these questions as we can during the Q&A after our presentation. If you have any technical difficulties during the webinar, just type your issue into the Ask a Question box and a member of our team will assist you. There are additional resources available from Teledyne E2V, as well as a copy of today's presentation in the Event Resources area located under the Ask a Question box. If you are running pop-up blocking software, you will need to disable it to view the webinar, and in addition, it is recommended that you close down all other applications for better performance. For your convenience, this presentation will be available for on-demand viewing within 24 hours of this live event, and a reminder email will be sent to all registrants containing a link to the presentation for on-demand viewing. It will also be accessible from the Vision Systems Design homepage at www.vision-systems.com. So with all that said, Yoann, let's get started.
Hello, good morning, good afternoon. Thank you, Chris, for the introduction. And thank you all for attending this webinar about pulsed time of flight. Pulsed time of flight is a technology which is, as indicated by its name, a specific time of flight technology using pulses of light to estimate the distance of the object. At first glance, it can be seen as a very complex technology that is difficult to understand and to use. That is true in the sense that the technology is state-of-the-art and requires the latest technical advancement. However, we will see today that this technology is very flexible with features and capabilities that can reduce the complexity of the whole system, allowing it to be simpler and more versatile. To start from the beginning, this is the basic principle of time of flight. A light is emitted by the light source and is reflected by a target to the image sensor. The light source and the image sensor are synchronized, and they are both used to estimate the distance and to build the 3D image. Generally speaking, the formula of the distance is the following. Distance equals speed of light divided by 2 and multiplied by the time of flight. Now you can see a quick video which illustrates this principle. Time of flight is divided into two techniques. The first one is called direct time of flight. The principle of this technique is to emit a light and to wait for the reflected one. The time between the emission and the reception, delta t, allows to directly calculate the distance, hence its name. The second technique is indirect time of flight. This one will split the reflected light into several phases, which will allow to estimate the distance of the object by comparing these phases. We will see an example just after. Obviously, both techniques have pros and cons, but among others, we can say that the direct time of flight is appropriate for long distances, but requires a sort of scanning and has a poor dynamic, while indirect time of flight does a flash acquisition of the whole scene with a good dynamic and allows lower processing complexity. We will now focus on indirect time of flight. In general, multiple images are needed to compute the distance image. All these images are acquired with a certain phase with respect to the light pulses that are emitted. The light pulse duration is a key parameter because it will define the maximum distance and the best precision that is achievable. The shorter the pulse, the better the precision, but the smaller the distance range. After that, the sensor receives the reflected light with a delay of T flight. Contrary to direct time of flight, in indirect time of flight, we will not directly calculate this delay. Instead of that, we will compare the ratio of charges which are received in each tap or memory node of the sensor. Below is an example of algorithm that can be used to calculate the distance. A lot of algorithms are possible, each of them with pros and cons, but this one is quite simple and easy to understand. In the formula is the first part, speed of light multiplied by T pulse and divided by 2, as on the previous slide. The interesting one is the second part. You can notice that there are 3 phases used here, or actually 2 phases, plus the background that is used to remove the ambient light. After that, the ratio of charges that are captured allowed us to estimate the phase, therefore the distance. And if the object is farther away, then there will be more charges in phase 2 and less in phase 1, as you can see now. So the algorithm will detect that the T flight is longer, and so the object is farther. However, you can notice that when the object is too far, and so there is nothing in phase 1, it is impossible to estimate the distance of the object. That is why the light pulse duration is linked with the maximum distance range which is achievable. We just said that time of flight requires an active illumination to build the 3D map. So some interferences can happen when several systems are working in the same area because the light from one system can fill in the phases of another system, causing wrong distance measurement, which can quickly lead to collisions, accidents, or other big issues if an object is not detected at its real distance. We can, for example, think about markets like logistics, robotics, or obviously safety. To avoid that, unlike other time-of-flight sensors, the Teledyne one has a multi-system management feature embedded directly on chip, allowing multiple systems to work together in the same area without mutual interference and without any connection. Below, in the setup of the next video you will see, there are 2 systems working at the same time and looking at the same scene, so they will interfere. On the right side, you have a screenshot of the video with, on the left, the depth map, on the bottom right, the setup, and on the top right, the distance measurement of the ROI. In the distance measurement box, you will notice that there are 2 parts. The blue one is erratic, which is when the multi-system feature is disabled, but it is also what you would get with a sensor without any feature to manage interferences. The other part is the red one, much more stable, which is when the feature is enabled. Furthermore, you will see in the video some blinking of colors on the depth map when disabled. That is a consequence of wrong measurement. Let me just remind you that the colors are distance scale, not real color. And let's now see the full video. Pulse time of flight provides good measurement in all conditions. That is what we will see now. First, a bit of vocabulary to notice the difference between accuracy and precision, which are two different things. Accuracy depends on systematic effects that can be mostly compensated by a calibration, while precision depends on the signal-to-noise ratio, on the full well capacity of the pixel, and on the modulation frequency or on the pulse width, and can, for example, be improved by averaging. Let's go into a bit more detail on how the image is captured with one of the camera on the market, using a continuous wave technique with a 4 phases algorithm and a 2-tap sensor. First, the sensor does the acquisition and the readout of the phases 0 and 2. In a second time, it does the acquisition and the readout of the phases 1 and 3. Then the computation of the 3D image. With a 3-tap sensor using pulse time of flight, such as Teledyne 1, the acquisition and the readout of the 2 faces plus the background are done in parallel. Then the computation of the 3D image is done. This has several advantages. First, less light is emitted, which allows us to reduce the average power consumption, to emit more light to see further, or to increase the precision while staying safe. Secondly, since all the phases are captured at the same time, there are no motion artifacts. Indeed, let's assume that there are 3 objects in the scene we are looking at. During the acquisition of the phases 0 and 2, the scene is this one. However, if the objects are moving, they will be in another place during the acquisition of the phases 1 and 3. So, for the computation of the 3D images, there will be a comparison of the charges of the different faces while they were not seeing the object at the same place in the scene. Thus, all the zones circled with black will give a wrong and erratic measurement. In the previous slide, we talked about the continuous wave technique using 4 phases and 2-tap sensors. That is a technique which is used mainly on the market today, but it is not the only technique available. Let's now see the differences between this one and the one used by Teledyne sensor. There are 2 different methods to emit the light, the continuous wave and the pulsed light we are talking about in this webinar. Here you have the drawing of how continuous wave and pulse time of flight are working, and an example of the algorithm which is most used in both cases. The first disadvantage of the continuous wave is that its operation is more sensitive to the multi-system configuration we were talking about just before. Secondly, in continuous wave, the duty cycle is fixed and maximum, causing a direct link between maximum distance and disambiguity distance. On the other hand, in pulse time of flight, the duty cycle is configurable, so there is a flexibility to trade off average power consumption, safety, maximum distance, and disambiguity distance. Also, it is possible to modify the pulse width to set maximum distance and maximum achievable precision. Then, an important point is of course to build the 3D map. In pulse time of flight, 3 phases are required, and the Teledyne sensor has 3 taps, so only 1 image is necessary to get the 3D map. In continuous wave algorithm, 4 phases are normally required while standard sensor has 2 taps, so 2 images are necessary. Furthermore, dual frequency has to be normally used to manage disambiguation, so in the end, 4 images are necessary to compute the 3D image. This can lead to motion artifacts, causing wrong measurement. Another crucial matter in time of flight is dynamic range. Indeed, time of flight is intrinsically a very high dynamic range application due to the combined contribution of the reflectivity of the object, and the distance range required by the application. To illustrate this point, let's assume you have application 1 targeting the detection of objects with reflectivity between 15 and 85% and from 0.5 to 6 meters. And application 2, where you need to inspect objects with reflectivity of 1.8 up to 95% and increasing the maximum distance to 10 meters. In this condition, application 2 requires 26 times more dynamic range than application 1. Large enough to need way more than a good full well capacity in the pixel. Teledyne sensor embeds specific techniques to manage its huge dynamic range, making it suitable for most application cases. We show here an example of 3 captures to extend the dynamic range. This case illustrates what you have with standard readout. A first exposure of T1 seconds, followed by a first readout, then a second exposure on its readout, and then a third and last exposure on its readout. Note that the pixel is reset and exposure restarted after each readout. Also note that normally, exposure times follow an exponential law in HDR algorithm. With non-destructive readout, the content of the photodiode is sampled after the appropriate time, but exposure continues after that, without resetting the pixel. Therefore, total exposure time is not the addition of the 3 exposure times, but the longest one, as shown in the picture, saving a significant amount of time. These techniques allow total integration and readout time to be shortened, which increases the frame rate and contributes to a reduction in motion blur. Moreover, it provides very high configurability that can be used to find the best trade-off for every application. Now you will see an example with a video with target from 10 to 90% of reflectivity, a range from 1 to 9.5 meters, taken in our darkroom. Sensors made for continuous wave time of flight, of course, have HDR capabilities, but they are normally based on dual capture, which is not enough for many of the challenging applications in terms of dynamic range. You can see below 2 simulation examples with the objective to compare dual capture with multi-capture, targeting the same applications condition, up to 10 meter distance with reflectivity between 15 and 100%. On the left side is a dual capture HDR, mainly used in continuous wave time of flight. As you can see, the precision is degrading when the distance increases, so that is dispersion within the reflectivity range. On the right side, however, the precision is good and quite constant over the whole range. You can see that the most part of the noise is between 13 and 25 mm in the multi-capture HDR, while it is between 10 and 45 mm in the dual capture HDR. So both the average noise and the dispersion are much bigger. Also, you can notice that in the multi-capture HDR from 2.5 meters, the noise for all distances and all reflectivities is well below 1%, while it is not the case for the dual capture HDR. Lastly, the worst noise, either for low reflectivity and long distance, is almost twice in dual capture compared with multi-capture. Since an image is often better than words, let's see the differences between the motion blur and the motion artifact we were talking about previously, with an analogy in 2D. The motion blur is caused by the movement of the object during the acquisition. It leads to a distortion of this object, as it is possible to see on the first picture, where the person is playing with a badge, which appears a bit blurred. In 2D, it is like the second picture, where the fan is a bit blurred as well, but the shape of the object is still a fan. On the other hand, the motion artifact would be in 2D like a picture of the same fan taken with a rolling shutter sensor. In the end, the shape of the object appears as totally different and erratic. In time of flight, it is revealed by long distance measurement, as on the picture at the bottom left. The badge is blurred, but the measurement around it is also false, with totally erratic colors. Just a reminder that here again, the colors are not real color, but distance scale. So it means that the measurement of the distance is not right. With Teledyne sensor, there are no motion artifacts, since all the faces are captured at once. The picture on the left is taken with the Teledyne sensor, while the one on the bottom left is taken with a camera available on the market. Now, let's see the full video of this comparison between the motion blur and the motion artifact for the two systems. On the top is a grid level image of the scene. On the left side is a camera from the competition, and on the right side, the Teledyne one. Pulse time of flight is a technology that can be very flexible. Obviously, it also depends a lot on the sensor, but at least the technology allows a nice flexibility that Teledyne decided to also implement in its time of flight CMOS sensor. One nice feature is the possibility to change the configuration from frame to frame without restarting the sensor. Here you have a drawing with two measuring sequences that can be different. It can be used, for example, to achieve a better precision even with a big range. Indeed, as we saw before, both the precision and the distance range depends on the width of the light pulse, but in an opposite way. So if you want to increase the range, you will basically need to reduce the precision. However, with the flexibility of the Teledyne sensor, you can program several measuring sequences with different characteristics and parameters. Below is an example where the first measuring sequence is looking at a long range from 1 to 10 meters, and so with a reduced precision. And when something is detected into the range, the sensor switches immediately to the second measuring sequence, looking at a shorter range of 4.5 meters, for example, so with a higher precision to better estimate its distance or its shape. First, it allows us to reduce the light pulse width and so to increase the precision of the detection, but it also reduces the required dynamic range because the distance range is smaller. But in the end, an object can be detected over the larger range from 1 to 10 meters. And when the object is moving, it switches to another configuration to track it. This was an example of flexibility in 3D, where we switch 3D frame from one to another. but it is also possible to interleave 3D images with 2D images. Let's reuse the previous example. First, the camera is looking at long range from 1 to 10 meters. Then, an object is detected by the system. However, the precision is not very high since the distance range is long. So, the sensor switches to another configuration in order to take a picture or a video in 2D, which can be, for example, capturing only a small distance interval around the detected object. This is called range gating, and it allows to avoid seeing non-interesting objects that are known as out of the range, selecting only the interesting one. In this example, only the cat would be on the picture, while the bird and the dog would not appear because they are out of the range. This is something that is, for example, very interesting in applications like outdoor surveillance to see better through the fog. Pulse time of flight enables multiple applications for different markets. It is convenient for applications from short range, like factory safety, to long range, such as robots for factory automation, combined with small field of view, like robot navigation, or big field of view, such as construction building mapping, and with small to big reflectivity range. It works both in indoor applications, like in pick-and-place robots, and in outdoor applications, like surveillance or ITS. As we saw before, it is suitable for applications where several systems are working simultaneously, like automotive, and also convenient for applications where a combination of short or long range are possible, like warehouse logistics management, thanks to the flexibility, allowing us to change the configuration from frame to frame. We saw that pulse time of flight is useful in a large variety of cases. However, even if the sensor can be the same in all cases, a lot of things need to be adapted at system level to match with the parameters. For example, the lens to fit with the required field of view. But if the field of view is modified, it has consequences on a lot of other parameters. The precision, because the angular resolution change, the distance that's achievable, because for the same power of light source, the light that is emitted per solid angle change, and so it also changes in terms of safety. And if we want to change the light power to compensate a bigger field of view, it will have effect on the precision, the distance, the reflectivity, the safety, etc. Here you have a table summarizing all the links that can be direct or indirect between internal and external parameters of a system based on time of flight. So in the end, it is not straightforward to estimate the output parameters of a system without a complete study, and many of these parameters need to be traded off. That's why Teledyne developed a time of flight model to simulate the specific application of our customers based on their specific needs. The results of our model will give the precision versus the distance for all the reflectivities, the frame rate, and the average light power, which is required to fit with the requirements. The main objectives are to support our customer during their assessment and dimensioning phases, or to support them for customization, both at sensor and system level. We can simulate, of course, with our sensor, or for custom one if necessary. To conclude, I understand that at first glance, all this flexibility may sound very difficult to manage, but it is not the case. During the previous years, Teledyne has built a multidisciplinary team ready to support you to make the most reliable measurements in any condition with deep understanding, not only at sensor level, but also in all aspects involved in the development of a time-of-flight system, including optics, algorithm, time-of-flight, and safety modeling, etc. For example, we have built a 100 square meter fully compliant laser-safe facility with suitable coating to avoid reflection in near-infrared and visible light. It has been operational for more than 2 years and was conceived to be used with an agile methodology. It allows us to calibrate our evaluation kits and future systems to deliver live demo and training to customers, but also to facilitate the validation of customer requirements and to develop and contribute to the standardization of distance measurement based on time-of-flight techniques. Here are some pictures showing the darkroom itself, the 10-meter motorized bench, and the light sources emulating the sunlight. To conclude this webinar, we will show you a video combining some of the important points we have seen today, such as the high dynamic range, the absence of motion artifact, but you will also be able to notice the high resolution and high speed of Teledyne time-of-flight CMOS sensor. Then, during the next 20 minutes, we will try to answer some of the questions you asked in the chat. But if you have more questions regarding the webinar, or more generally regarding the technology or time-of-flight, please do not hesitate to contact us, and we will be more than happy to work with you to find the best match for your application. Thank you.
Okay, perfect. Well, thank you, Yoann. For that, we do have a number of questions that did come in here. So let me just get back to that screen. To get us started, what is the maximum distance that you can achieve?
So for the maximum distance, actually, so virtually, with the sensor, there is no limit. The limit will more be with the precision that you want to achieve, and also with the safety that you have to respect. For example, if there are people working around, you will need to be safe. However, in some applications like I don't know, in space or in mining where nobody is working, you can have a more powerful laser, and so you can emit more light and to see further. But the limit comes from the system and not exactly from the sensor.
Okay. What is the data that emerges from the device?
So it can be different things. When we are talking about the 3D image, we are the data which is given by the sensor is the information for each memory node or each tap of the sensor. So you get in the end 3 images, one for each tap. For 2D, it's directly the gray level image.
Okay, now I'm going to do my best to get this right. This is a little bit of a long one. It looks like, let's see, how is the accuracy and precision of the camera and chip compared with continuous wave compared with a continuous wave time of flight chip, given that continuous wave typically runs at a much higher modulation frequency?
This is something that is difficult to answer without knowing the characteristics and the parameter of the application. It can be very different. So I cannot answer this question without more information.
Okay. Let's see. Could you talk about the advantages of your HDR compared to other choices that folks could make?
Sorry, Chris, can you repeat the question?
What exactly is the advantage of your HDR compared with other options?
Oh, okay. So first of all, as explained in the webinar, so we have the non-destructive readout, which allow to reduce motion blur and also to save time. And so this combined with high frame rate that we have in the sensor, so it's more than 400 FPS considering only the readout. So after it depends on your exposure time. We can use this time to perform averaging, for example, to increase the precision, or just to have a final higher frame rate with the whole system.
Okay. Let's see. What kind of parameters can you change from frame to frame, and how much?
So we can change a lot of parameters. It can be the ROI size, so both in column and line. We can change the exposure time. We can change from 2D or 3D. We can change the binning if we want to put binning in the image. And how much? Virtually there is no limit, because the sensor embeds two memories, and we can read one memory while writing on the second one to put the parameters of the sequence. So in one memory, we can put up to 170 sequences, different ones, if we consider the short one. If the sequence is more complex, it's less than that, but we can put up to 170. But if we are using sequences from memory now, one, for example, to run the sensor, we can write in the memory two at the same time. And so we can switch to one to another and put it live without any or it's not necessary to restart the sensor.
Okay, another one came in. Can pulsed, I'm assuming they left out the time of flight. Can pulsed time of flight capture supersonic moving objects?
So I'm not sure, but definitively it can be analyzed together with other application level requirements. But theoretically, that could be possible.
Okay, could you talk about the software that you would need to process the data?
So for the software, it's more to be seen at system level, but it can be a lot of software.
Okay, let's see. I believe this is a follow-up to the continuous wave question. What is the range of modulation frequency for this?
So in pulse time of flight, the important point is not the modulation frequency, but the light pulse and the transfer time. For our current sensor, it's 20 nanoseconds. So, and in the future, it will be more 10 nanoseconds.
Okay, let's see. You touched on this toward the end of the presentation, but wanted to see if you could revisit it as well. What are some of the applications for which pulse time of flight is particularly suitable?
So it's particularly suitable for fast-moving objects, or when the application embeds a fast-moving object or scene, thanks to the dynamics and to the simultaneous phase capture. So as we saw in the drawing before, so there is no motion artifact with our sensor and the pulse time of flight. And so even if there is some fast-moving object like robots, or we can also think of automotive surveillance, there is no wrong distance measurement in the final image. And so it's much easier to recognize the object and the shape than with other techniques who suffered of motion artifacts.
Okay, that about does it for our questions today. And with that, we've come to the end of our program. As I mentioned at the start of this event, this session will be archived for future access, which should take place in about 24 hours. All registrants will receive an email with a link directly to the archived webinar. So please feel free to pass this link around to your colleagues. You can also access the archive at www.vision-systems.com. Finally, I'd like to thank Yoann today for sharing his time and expertise with us, our sponsor Teledyne E2V for making today's event possible, and of course you for attending. We look forward to seeing you at our next webinar. So until then, have a good one, and we'll see you soon. Thanks again, Yoann.
Thank you, Chris. Thank you, everyone. And again, if you have more questions or if you need more details, please do not hesitate to contact us. Thank you.